as she said, I'm going to talk today about utilizing large-scale randomized response at Google. So this is a project called RAPPOR. It's still going on, still going strong, and I'll also talk about some of the lessons we learned in deploying this, designing it, explaining it to people, and so on. So as you can clearly see, this is work done by a lot of people, and the author list is sort of purely chronological, not in order of contribution. So, and there have been some lot of fantastic experts who have helped us with all these things, including Ilya Mirno, who's one of the people who's sort of been there with differential privacy. So this is work done with a lot of very smart people, very interesting people, and I'll just be here sort of talking about it. So let's get started. So why did we do RAPPOR? So why talk about differential privacy? Why implement anything in a company like Google? We were interested in finding out what's happening with Chrome. So Chrome is a very popular browser. There are a lot of people using it, but this also means there are a lot of people abusing it. There are a lot of hijacked instances, malware, bad extension, things of that sort. And one of the first things that they do is they go and muck around your default homepage so that you think you're talking to Google or you're sending all your queries through Google. But instead it's going through some other random server farm. There are being ads that are served that are mostly malicious, things of that sort. So tracking some of these is really challenging to do it out in the wild. And we wanted to find out which Chrome homepages and search engines were being used by clients. Just in general to have an idea to make sure that this is sort of matches what we expect out there in the wild. So doing this, well, you could just collect all the URLs of all the people who use Chrome, but of course that seems kind of privacy invasive. So instead what we decided to do is to design an algorithm to sort of find the popular percentages of things like Yahoo search, Bing, Google, of course, and also see if a bunch of bad guys show up there. What RAPPOR lets you do is to find this sort of information, so find this distribution of, say, homepages or kind of default search engines, things of that sort, without actually seeing any particular user's homepage in the clear. Here's another example of how RAPPOR is very useful to collect data. So engineers in Google, they love graphs like this. They want to really keep aggressive track of who's using what and sort of where things are going wrong, where things are breaking down. I think this is a couple of years back when Silverlight was still all the rage, but it was also very buggy and required a lot of work to sort of fix and to keep stable. And we wanted to estimate, for example, what were the big websites that were actually using Silverlight without actually getting into details of exactly where you used Silverlight or which URLs maybe showed up using Silverlight. And I'm sure there are a lot of very interesting places on the web that use Silverlight that you probably don't want people to know that you're using. So I'll leave it at that. And you can see some interesting trends here already. You can see, for example, Netflix was working with us, and it sort of dropped off pretty fast. I think once they reached some internal deadline. This is the blue bar going down. And you can also see Intuit, if you sort of look through the maze, which is the yellow bar, actually rising up past mid-January, which was sort of tax season. So people suddenly started using a lot of Intuit, I presume. And that actually was able to show up in our dashboards. And all this data is estimated with differentially private techniques. And you're collecting millions and millions of records to do this. And here's a nice metaphor for RAPPOR that one of my co-authors thought of, and I think it's been very useful explaining it internally. So imagine you want to find out a sort of a big picture of the world, and imagine it looks something like this. So it looks like the Mona Lisa. It's made up of a lot of individual information. So this is sort of an individual report that comes from a particular user. Without any noise, you can see it's maybe privacy invasive. It's quite revealing. You can see here that it's an outline of something, probably a finger. There's a background. There's sort of a lot of white space, things of that sort. And you'll see that we really don't care about details at this level. What do we do? Well, we maybe add some noise to this. So we flip each bit with, say, a 25% probability. And an individual's report looks something like this. So you can see here that it's still kind of noisy. You really can't make out a lot. However, if you aggregate everything together, and I hope you can kind of see it here, sort of the big picture still remains. So maybe this whole metaphor is just to kind of come out with that phrase, that the big picture of the whole world kind of remains. But you can see that this is actually a pretty effective way of showing that adding small amounts of noise locally does not actually destroy the global structure. And in a lot of applications in practice, for example, the two scenarios that I gave you, so looking at Silverlight data or looking at Chrome homepages, things of that sort, individual data. So when you don't have good accuracy about what say 10 users or 100 users used, that really doesn't matter. The big picture is sort of what we care about, and we don't need to break users' privacy collecting all this sort of personal data just to get the big picture. So this has been a very useful metaphor to explain to people who don't understand differential privacy or who don't generally understand why sort of these noisy things have got to do with privacy and how it's actually doesn't screw up all the analysis because, well, I mean, people hate noise in general when you're trying to do data analysis, and what they want is to sort of aggressively remove it, right? So it's sort of counterintuitive. But this has been a very useful way to explain it inside as well. I also want to note here that there are a lot of things that are going on at Google that we sort of we do for protecting users' data. So when we're collecting data, we scrub IP addresses, timestamps, things of that sort. Typically, we keep central databases of scrubbed data, but only for a very short period of time. And we only report aggregates of data over a particular threshold. So we need to make sure that even in places where we don't actually use privacy-preserving techniques, such as RAPPOR, we still have a pretty good defense against sort of privacy invasion. And in a lot of cases, this is the best approach. So differential privacy or randomized response, or even some of the other awesome techniques that people have talked about and researched, some of which you heard yesterday, I'm sure you'll hear a lot more today. They don't always work for everything, so it's not a big hammer kind of to solve all the problems. And in some cases, we actually end up recommending people to use something like this for different cases, for different use cases. So if you have opt-in users, for example, so where people are explicitly giving you consent, then it's usually OK to try to have these best practices. Sometimes there's low sensitivity data. There are people who want to know something that's happened like with a very narrow sort of confidence interval and with very sort of a lot of accuracy and precision. So things you can imagine, like there are certain bugs that hardly ever occur. But if they do occur, you really want to keep track of it, because that is very fundamental and very critical. And you can't just throw it away because it happens very infrequently. So in these sort of things, low sensitivity kind of data that's, or maybe it should be high sensitivity, I'm not quite sure. It's very difficult to actually learn this with privacy, because fundamentally the data collection is at odds with privacy. However, there are a lot of other cases where things like RAPPOR are very, very useful. So one of the this is kind of the plus points, or the selling points of RAPPOR, is that we have rigorous and meaningful privacy guarantees for every user. So you can actually talk about a particular user's data, give them some notion of differential privacy. You talked a lot about differential privacy yesterday. We can actually give these epsilon values, so that's fantastic. Not a lot of systems out there that are deployed in practice do this. We don't have a central database of user data, so there's no particular central point where all the privacy-sensitive data lies, and then we need to worry about maybe that being hacked and leaked, or maybe there are subpoenas or other sort of things that happen. Users' privacy does not depend on a trusted third party, right? So we don't say you're going to trust some external person, or you're going to trust someone else that's not part of Google, things of that sort. And an interesting use case which I'll talk about is we also have to design this such a way that by deploying this scheme, we don't actually introduce additional privacy externalities. So there are many ways where we might maybe want to track users with unique IDs to make sure that they're not giving too much data. But in the process of doing that, you end up actually breaking the user's privacy, because you end up tracking them. So we need to be very careful about these things. And it's sort of very well suited to sensitive user data, such as URLs, where there's not a lot of structure to the data. But we also get this from millions of users. And this is an internal slide. So RAPPOR also kind of gives you a nice dashboard, like you saw in the first couple of slides. It's very useful because this is sort of what people look at. So they're very happy to see a dashboard that looks like this. They say, OK, here are sort of the list of Chrome home pages. And obviously, the y-axis has been redacted. But it gives you percentages of, well, how frequent are Google.com and MSN and AVG and all of these home pages that are sort of like your default page. And it's good to see Google is up there. And you want to make sure that nothing funny happens here, for example. And the usual suspects, like Google subdomains or the Microsoft or Live, things of that sort, they are at their right levels, so that we make sure that there's no instances of sort of hijacked Chrome instances out there with like their own web pages that suddenly show up. Because if that happens, we need to go and find out and fix it. So this is a slide that sort of my manager uses. He's a programming kind of security background. So I'll just try to express it in my own words. The way we explain security and privacy to people is we sort of talk in the language of programming, which is much more common for engineers, for developers. Typically in programming, you have sort of specifications for what you want to do. You have implementations that try to implement this specification. Then you have a correctness, a way of sort of verifying that what you've done is correct. And finally, you have a methodology where you talk about all this, right? So you talk about functional programming, and they have their own quirks with correctness, implementations, how you describe specification, things of that sort. So similarly, in the security world, we have security policies. That's very kind of, everyone understands that. Everyone understands what enforcing a security policy means, like through audits, through EULAs, things of that sort. Then you have this assurance that, so you, again, like kind of you look at audits, you kind of look at, there are teams that do sort of red team attacks, things of that sort. And finally, you have a security model where you talk to experts and you say, well, we're going to describe this, these are the adversaries, or these are the boundaries, these are the trust issues, things of that sort. And that gives us a framework to discuss all of these things. Sometimes we try to explain privacy in that way. So we say that local privacy, local differential privacy, or any other sorts of differential privacy is not a technique. It's not a catch-all solution. but it's a methodology. It's a way of talking about what we are doing to preserve user privacy. So with that, we need to talk about the privacy policy. So Chrome has a pretty good privacy policy that talks about how and when user data is collected, things like URLs, what we use that for. So sometimes you use it for kind of exigent circumstances when there's maybe risks. When you're trying to go to a phishing web page or a malicious web page, then immediately we get some information to make sure that you don't actually visit such a web page. But we also use it in general to keep track of the global sort of ecosystem. So that's a privacy policy, and there are enforcement mechanisms because it is a Google product, and we have sort of our own privacy sort of infrastructure across all products. There are some assurances that we give both internally to teams, lawyers, and externally to customers and I guess regulators, things of that sort. And the privacy model is sort of the methodology here. So people understand things like HIPAA, so they understand that this is the language in which we need to talk about what we do with user data. We want to bring local and database differential privacy to sort of that extent. We want to say that this is a way of talking about all of these problems that people have thought about, people have implemented good solutions, right? So it's not that no one cares about privacy before local privacy or differential privacy came about. But this is a new language to talk about it, and it looks like it's a pretty good language. So it's sort of the gold standard. There are a lot of these nice properties, this composability. There are concrete, rigorous guarantees. It's exciting. It's a lot of nice technology. So that's sort of how we're looking at it. So I just want to kind of summarize the talk. So it's going to look like this. So you're going to have a few takeaways. You'll learn about randomized response. So what exactly is the technology behind it? In particular, we'll talk a little bit about this Rapport's 2-level randomized response. So it's a very interesting, it's a twist of classical randomized response and why we designed it that way. I'll talk to you about some lessons learned from a large-scale deployment of such a scheme, and then just briefly mention some follow-up works. So just to talk about other things that are going on at Google. So randomized response, I think this was mentioned yesterday in someone's talk, which I don't quite recall, but it was a survey technique that was developed in the 60s, and this is a canonical example, like, are you now or have ever been a member of the Communist Party? And interestingly enough, if any of you have been dealt with immigration today, you'll know that they still ask you questions like this, and they don't let you flip coins and things of that sort. You just have to answer. But in the 60s, they really wanted to find out such sensitive information. And people who had these sensitive surveys, they wanted to get good data. So they came up with a good technique to make sure that people are incentivized to actually participate in the surveys. So what do? You flip a coin in private, and if the coin comes up heads, you respond yes, always, so independent of whether you're actually a communist or not. If the coin comes up tails, then you actually tell the truth. Now you have this plausible deniability, right? So you have some amount of, you can tell a story. You can say that, oh no, I'm not a communist. Actually, the coin that I flipped came up heads, and you don't know because it's a private coin. But for people who actually need the data, you can get a good estimate by just simply doing some basic arithmetic. You can find out a good estimate of the number of communists that are out there if everyone responds truthfully through this sort of system. And then it turns out that actually just from the starting point, you could quickly get differential privacy. So back in the 60s itself. So if you just flip another random coin, and instead of always returning yes, so you kind of have a two-sided error, you return yes with some probability and no with some probability. And if the coin comes up tails, you sort of tell the truth, it actually ends up satisfying differential privacy. And it's still easy to estimate the true yes ratio depending on these parameters, and that also sort of informs your differential privacy parameter epsilon. So it's a pretty powerful technique, and it's also easy to explain. And we use that as a starting point. And what we did is we extended this randomized response to sort of categories. So now imagine you have a bunch of yes or no questions. They're all done in conjunction. Think, for example, salaries. So you have buckets of salaries. So you have salary ranges from 0 to 20K, 20 to 40K, things and so on. And you basically have yes or no responses to each one of them. It's also important that you only respond yes to exactly one of them, so that you sort of affect the sensitivity of the functionality. You can just simply do bit-by-bit randomized response. And it turns out that that's still powerful, and you can still get things like averages of salaries, salary estimates, sort of a good estimate on the max and min and things of that sort. So here's an example. So if we see a bit vector that looks like this, it's not clear whether the user's salary is actually 1, or it just happened to flip a coin and it shows up 1 here. So it provides you some amount of deniability about what a user's actual salary is. So this is from the paper from a few years back, where they ran some estimates based on, I think, noise parameters that were very, very generous. In other words, you got very good privacy. And we could see that around 10,000 users, there's still a lot of noisy estimates. But around 100,000 and 1 million users, we start to get, say, a Gaussian distribution of salaries quite fairly accurately. And there are some small errors that are there in the tails. And it's very important to explain to people that sort of these errors in the tails, they must remain because they have to protect user privacy. There could be someone who has a salary that is quite significantly outside, and there's really no accurate way of telling yes or no because that would break that user's privacy. So this is just a very typical estimate that says that as you collect more and more data, you can get better and better concentration bounds, and you can actually estimate true values through randomized response fairly accurately. What do we do with this? So we have a randomized response for categorical data sets. Well, we can use this to actually represent much larger data sets. So one of the main challenges in a practical deployment of something like this has been that the data is fairly unstructured. So when you have something like URLs, well, they just want to collect as much information about URLs as you want. So either hosts or just the top-level domains. Maybe sometimes they also want to have little snippets of all the parameters that follow through, things of that sort. So that's quite challenging. There's not an easy categorical representation that's just a bunch of yes or no questions. So what the paper did was they said, hey, well, how do we represent large data sets? Well, we can try to use Bloom filters. Bloom filters sort of reduce an arbitrary data set into a bunch of yes or no questions. And then we also have some other tricks. Typically Bloom filters, they have collisions, they have false positives, right? And then what we try to do is we just try to use many Bloom filters in parallel. And we just choose to report one of m possible Bloom filters, which are called cohorts. And as I mentioned yesterday, I think the discussion, such techniques were pretty useful because if there were some rogue reportees out there, the fact that we split this into several cohorts, so we run multiple things at the same time, kind of let us know whether the data is accurate across, if the data is correct, reliable across all of these cohorts. So it helps us with false positive, but it also helps us sort of verify that our data, which is noisy and we don't have the true distribution because, well, by definition, we are not supposed to have the true distribution, but we can still kind of give some quality estimates about this. But we used the cohorts to try to minimize false positives, and each cohort kind of uses a different Bloom filter hash function. So you can also equivalently think of this as having a really large Bloom filter, right? And then you just report one subset of it. And the subset that you report kind of depends on your unique, say, Chrome ID or your Gmail account or things like that. So it's something that's secret. You don't actually report it. You just derive a cohort out of it and use it. So that's basically the high-level thing. So we have URLs. We hash them to a Bloom filter. We kind of get a big bit vector. We choose some subset of it consistently, and then we add noise. So what is this two-level randomization business that's going on? So one of the challenges I think that's not been fully fully explored, or there's no clean solution, at least out there in the community, is the academic community, is what happens if we have time series, or what happens if we need to do these analysis consistently? So we need to kind of repeatedly ask the same question again and again, right? So people are not happy with a single snapshot instance of the view of the world. They want to see how it evolves. They need to ask the users the same question again. And this affects privacy in kind of obvious ways. So for example, if you're talking about the coin trick, for example, it's easy to see. So that if you ask the same user several times and they keep flipping dependent coins, then it's eventually going to converge to their true value. So if you ask the same person, are you a communist like in 1960, 1961, 1962, and so on, quickly you're going to figure out that whether that person is actually a communist or not if they flipped independent coins each time. So to avoid these sort of things, and the same attack applies here. So if we end up collecting data from the same user over and over again with independent randomness, we can kind of quickly converge to the true Bloom filter values without all these noise. So what we do is that we basically keep track, or we remember what were the coins that were flipped. So we reuse the same answer over and over again unless the underlying value changes. And as long as the underlying value does not change, you basically cannot get this sort of averaging attack on coins that are flipped. But this leads to its own challenges. So well, if we kind of keep track of a long Bloom filter that has a bunch of random bits, then it's basically a random ID, right? And this ID itself can hurt anonymity. So this long repeating bit sequence forms a unique tracking ID, and in the whole kind of purpose of trying to provide privacy, now we end up tracking all the users in Chrome, which is a big no-no. So there was these two levels of responses that are required because we did not have any way to actually provide anonymity to the users. So we're collecting information from them directly. We have their IP addresses, and IP addresses and things like that are stripped off at an earlier stage. But when you have this big database, remember we had this database of random bits, we didn't want to have these unique IDs that were there all over the place. So the solution was to apply randomized response once more. So we have basically a long random bit vector that has some information about your URLs, for example, or your Chrome home pages. And we don't want to report this a long random ID over and over again because it becomes a tracking ID. So instead, we do randomized response on top of these bits again. So we have 2 levels. This just basically adds more noise. So it's a fancier way of saying that we add a lot more noise. And then we report coin flips on this sort of memoized data. And it turns out that in practice, depending on the amount of noise you add and how big these unique tracking IDs are, it's pretty useful. You get a good balance between privacy and utility. So here's how the algorithm looks like. So you hash a value into a Bloom filter. It's very simple. Using some h hash functions, where this is a parameter. So we use like 2 hash functions. It provides a good utility. And then we memorize what we call a permanent randomized response. So this is kind of your true value that you never ever go below this. So you never actually report your actual value v. You always start off with a permanent randomized response. And then you report something which is called an instantaneous randomized response, which actually flips bits with some probability q and p. So this sort of sets 1 with a higher bias q and a lower bias p if the underlying permanent randomized response is 1 or 0. So I'm just sort of reiterating what I said in the previous slide in an algorithm. And here are some sample parameters, the default parameters that we use in Chrome. And I think if there's time at the end of the talk, I'll actually show you some values for differential privacy, what values these provide. But this is actually there out there. You can look at the Chrome code. You'll see some of these values show up. And in the Chrome experiment, we also had an open source project. So we try to maintain this project at GitHub under the Google directory. I encourage all of you to kind of take a look at it. You can run some demos with some simple shell commands. There's a client library that you might want to look at for Python code and things of that sort. It's a bunch of documentation. It's not complete, and feedback is like always welcome. But this is sort of what the scope of our project was, and we can get these nice cool graphs that show how true distribution, for example. So the blue values are the actual distribution, and the red values are what RAPPOR actually estimates. And you get pretty good estimates, and you can kind of see a little bit into the tail, but not entirely, obviously, for privacy reasons. Okay, so this is what was the design of RAPPOR. So what was the motivation? How we went about starting with randomized response? What were some of the challenges that we faced with trying to make sure that we didn't have unique identifiers, kind of the 2-level response? What did we learn from all of this? So what are the lessons learned from this? Well, the first thing is sort of you want to design. It's very useful to design things with explainability in mind. So this is often not a criteria that we have in research. It's not often a criteria that we have when we think about designing things. But I think one of the most important factors for success, and some people might argue it was too successful, and I'll get to that in a while, was that people kind of understood what was going on. It was very easy to say, oh yeah, we have this data, we have a bunch of Bloom filter bits. It really doesn't look like a URL, so there's not a lot to reveal there. And then we add a lot of noise. So you can look here that in some of the demos that we showed, that we are basically flipping like more than 1 in 2 bits. So there was a lot of random bits that were added. And people are able to understand that, okay, this is all that's going on the client side. This is all the processing that happens with user data. And, well, maybe that's okay. Maybe there is some privacy that's going on there. So explaining designs to users, to lawyers, to people who are involved in the policy side of things, people who want to actually kind of design this as part of a broader strategy, a broader story about privacy at Google, it's very useful to have simple and clean, easy to explain designs. We also need, obviously, reasonable epsilons, and we might want users still to opt in anyway, because at least in a company like Google, in the scale of Google, opted in users, there's still a big population to work with. So that was something that was done, I think, quite deliberately by Ulvar, who started this project, and it was a very useful, kind of useful thing. That there will be a lot of growing pains. So I was involved in taking the research prototype to actually maintaining a real product. And I think one of the challenges are that when we do research, we are sort of, we don't work in the mindset of actually maintaining a system that's supposed to run for years and years. There are certain issues like scalability that are not immediately thought of because things scale to huge, massive amounts. We get a lot of data, but we also have to work with a lot of data. For example, some of the constraint satisfaction things that we had to do involve hundreds and hundreds of variables, and then we had to kind of re-engineer a whole system to get it working again once you sort of hit critical mass. And these are things you don't think about when you're only focused on the privacy aspects or only focused on sort of deploying cool algorithms. And versioning, I think, is very important as well. So when you design and deploy a privacy system, there's obviously going to be feedback. Some of the parameters are not going to be accurate. There's going to be some challenges where people wanted more data or people are happier with less data. And you want to quickly start versioning things, but you don't want to have too many versions or too many experiments going on, because that itself leaks information. So which version you're actually reporting, what version of software you're using, all of these start to become unique identifiers. So you have to be very careful about this, and you have to design it in such a way that, like, maybe we need to do some sort of privacy-preserving analytics on the way we're actually collecting privacy-preserving data. So we need to have this 2 layers of thinking about things. Things will go wrong, and we need to sort of figure out how to correct them without actually breaking everyone's privacy. Communicating uncertainty, I think that's a very important lesson. So people were not very happy when we gave huge error bars, and we had to spend a lot of time to explain to them that, well, the underlying data is going to be noisy, right? There is going to be some sample variance in itself, but differential privacy and any sort of privacy technique explicitly adds noise to it. So explicitly adds some uncertainty, and it's very useful to demonstrate it concretely through graphs. And then people can sort of either take what we have or just leave it and say that this is not sufficient for us. So we had to update a lot of our graphs to explicitly show uncertainty, and many people were very uncomfortable when they actually saw the amount of uncertainty that was involved when you had these error bars. I think this is also very interesting. I think there's not enough research done here. So we have some ideas. We haven't actually written it up. So I'm not sure how much I can talk about it in too much detail. But in RAPPOR, we have this notion of a candidate list of URLs that you need to start off with before you can actually learn information. So in other words, you need to have some guess about what is the population of URLs that people are reporting from. But luckily, we are Google, and we do have a good estimate of what are the URLs that people are typically visiting and reporting from before we actually feed it into the system. So we need these candidates. So these are not actual data, like this is not user data, but just a candidate list of what are possible strings that will show up in the distribution. Sometimes we go wrong with this. Sometimes there are some use cases where we don't have a good estimate of what the URLs are being reported or what strings are being reported. And it turns out that if we look at the way differential privacy is designed, we can look at something called residuals. In other words, we can look at, once we get our estimates, we can go back and see how the data should have looked like if our estimates were actually true, and then see what the kind of the counts or the totals look like. And they typically should look like a Gaussian that is distributed around 0, because that's how noise is supposed to look like, right? So you're adding noise to a true distribution, and it looks something like this. So typically, if our data is good, then we have a sort of nice distribution, a nice Gaussian here. But if the data is bad, then you end up with this sort of wonky distribution where every single little peak here actually reveals some information that there's some underlying data out there that we are not able to see. But by definition, we actually don't know what the data is because we are collecting things with privacy. But you can at least go back to teams and say, hey, you know what? Your estimate of kind of the data that you're collecting was not that accurate. And so this is an example where there were, I think, 3 missing candidates. And we had to go back and work with them to say, oh, maybe you missed this particular URL, or maybe there are certain constants and hard-coded strings in your code that happen to show up from time to time, and we are collecting them by mistake. Things of that sort. So designing a privacy scheme where we keep in mind things that go wrong, things will go wrong, and to collect diagnostics on how things go wrong without actually breaking users' privacy, I think that's a very useful thing. And there's a lot of work to do here, actually, even in just randomized response. And then there's this thing about knowing your enemies and friends. So if in a company like Google, there's a lot of data being collected. There are many teams that have their own way of working with things. If raw data is being collected already, then privacy people and any sort of technology is actually a hindrance to utility, right? So it's sort of, you are already collecting data, you already have sort of a pipeline that's going through, and now if you want someone to say, hey, you know what, we're going to screw everything up, we're going to add some noise, things are not going to be that accurate, people are a bit resistant, or they're not quite on board as we would like them to be. And it's also very hard to avoid the slippery slope. On a more sort of principled way to look at this, if there is a corpus of raw data sitting somewhere, however protected it is, there's always a temptation to go and ask for more. It's always a temptation to say, hey, you know what, we collected this data, it's not sufficient, can we go and peek at it some more? Can we kind of keep poking at it more and more until sort of the dam breaks? So it's very hard to avoid the slippery slope when there is actual raw, really good data that's privacy invasive sitting anywhere. So this is kind of a challenge for pure sort of differential database-based differential privacy techniques. So these things where you have accurate data sitting somewhere, then you just gate wall queries, and you make sure that you keep track of kind of how many queries are seen, things of that sort. That might be a little challenging in practice. However, if you're collecting data that you can't collect anyway, but you collect it from the ground up with sort of local privacy, so you get only statistically or privacy protected data, so you only get noisy data, otherwise you don't get any data, then then the sort of equation flips around. Then the privacy people, the ones who understand what are privacy parameters, what is the best sort of noise to work with, or best statistical techniques to work with, then we actually become critical to utility, right? So the more you interact with privacy people, the better utility you get out of it for a given privacy level. And this is a big step up on the slippery slope, because we don't actually have a corpus, or we don't actually have a database lying somewhere that's privacy invasive, or that's kind of very, very sensitive. So it's a good reason when you're working in sort of larger organizations and when there's sensitive data being collected, to start to discuss privacy very early on, to start to add noise as early as possible in the pipeline. And then, well, you need to have a lot of friends, and you need to keep your friends close. So you need to partner closely with users. You need to monitor their use. So you can look at this XML file that's there in the Chrome source that has all the teams that sort of added RAPPOR, and a lot of them added RAPPOR as a black box. So that's what I said when I said that the technology was too easy to explain, and people thought that it sort of solved all their problems. They started using RAPPOR kind of as a black box, and they ended up being disappointed. Well, because privacy is the randomized response is not a catch-all solution. There are some cases where it works really well, some cases where it does not work that well, and some cases where it's just completely the wrong tool to use. So sort of avoiding users from treating your technology as just a sort of plug-and-play system is very, very important to get across. So when people talk about privacy and data collection, they need to understand that it's not just something that you add on at the end. It's something that you think about from the ground up. It's something you think about when you think about data collection. And then to sort of sum up all of this is basically you want to set and manage expectations with people you work with closely. So you want to make sure that privacy inherently means that you can only look at sort of the tops of distributions. You cannot look deep into the tails. You cannot find one-off events that might be very useful for your debugging purposes, but, well, that's antithetical to privacy. So setting and managing these expectations is a very critical part of making sure that not only do people use your technology, but that you also understand sort of where your technology needs to be used. And finally, the world sort of depends on trust. So in the entire story, Google is the one that's actually providing all the code for Chrome, providing all the code for RAPPOR. You completely trust Google if you're using Chrome to actually do the right thing. So there is some trust, and we can actually leverage this trust. So the part of the story you could say is that things like techniques like differential privacy, they are sort of worst case fallbacks, and they are kind of defense in depth. So there's an extra wall to all the other protections that we do to give users good privacy protections. And we actually do much, much better unless sort of Google explicitly chooses to do evil, right? So we have a lot of audits, we have a lot of access control, things of that sort. So this is a good way to kind of good messaging system to get out there. And we need to work better kind of to combine trust and privacy. So maybe we need to kind of think about privacy not just from a technical lens, but also something where maybe there are contractual separations of domains. And so yesterday we saw these talks where there are multiple parties that are working, and there was some sort of domain of separation. That's something useful to think about, because there are contracts that do these kind of things in practice, right? There's all these industries that exchange data on a contractual basis. So maybe we can leverage that understanding that the industry has to give better user privacy. And this is, I think, something that my manager likes a lot, which is there are all these techniques about SGX and things of that sort, right? So where we have ways to have much, much more stronger kind of verifiable computing, things that make sure that we can give explicit proof as to what is going on in a user's computer. And it's useful to leverage that, because it's not just sufficient to say, hey, we are doing the right thing, but here's also proof that we're actually doing the right thing in terms of user data. So with that, I'll sort of conclude. I'll just give some pointers to follow-up works if you're interested in looking at it. So there's some work on trying to improve RAPPOR without these candidates. There's some work by Adam Smith and his folks on things and sort of providing bounds for RAPPOR, like local differential private algorithms for histograms. There's been some further work at Google. And finally, there's now everyone's doing machine learning these days, so there's always sort of trying to combine privacy with machine learning. So some of my co-authors have been working on trying to do deep learning or some other sort of knowledge transfer from deep learning using private training data, and we're getting fantastic results. And these are some of the things that sort of Google is actively investing in trying to make sure that user data is used kind of usefully, right, to provide users good utility, but also we are very mindful of privacy of the data. So to conclude in one slide, so RAPPOR is a locally differentially private mechanism for reporting categorical data and string data. That's what I explained. So as far as we think it's the first internet scale so deployment of differential privacy. We're collecting a lot of reports today, and we continue to do so. It was explainable, which was contributed to its success. It was kind of very conservative, so we failed in a lot of cases where we just didn't get enough data. Some of these error bars were just too big for people to use, but it was good to be conservative. It's good to be conservative in deploying new techniques on the scale. It's open source, so people can use it and modify it for their own purposes. It's also been very challenging. I pointed some of the interesting lessons that we learned. And of course, I think it's just the beginning. There's going to be so much more that's going on. And as you can see from yesterday and today and all the other sort of kind of burgeoning privacy stories, I guess, that are going out there, there's going to be a lot more that happens. So it's a very exciting time to be working on privacy and technology and things like that. So I conclude, and if there's time, we can take some questions here. And you can talk to me afterwards, offline, on why I have that email ID at Google. So.
So I have one.
Yeah.
So you talked about explainability and the importance of explainability, but you talked about it sort of within Google.
Mm-hmm.
So as you've been deploying this out to the world, do you
No, it's not just Google.
Customers aware, or like both sort of end users and any other sort of?
It's not just Google, actually. So the explainability has been on multiple fronts. So I think at Google, it's useful in terms of not just engineers, but like product managers, people who see it as part of their strategy for the product development. But we also did work, or by we I mean my manager mostly did a lot of work on messaging and sort of PR, where we actually talked to people, I think from the EFF or ACLU, I'm not sure, and we got them to understand that, I mean, this is what you're doing, and it's a pretty useful thing, because once you understand it and if you have some technology background, it's pretty useful, and it got a lot of popular press. And I think working through these sort of mechanisms to kind of do this requires something that's easy. So if you try to do something really complicated with, say, and not to name technologies, but like multi-party computation, or for example, there's some really fancy crypto that I would love to work on as a cryptographer, but that's very, very hard to kind of explain. Right. And we have to be very aware of that when you're designing these things.
Right.
Yeah.
And do you have, though, any messaging that goes all the way to like the end user at the browser, get more information, and they
not explicitly. So there is some slides that I sort of removed, or it wasn't there in this version of the talk. But we do have a license agreement, an end user license agreement, or we have a Chrome white paper on privacy where they explicitly mention that here's the data where we collect, and we actually use things like RAPPOR, randomized response, and there's a link to a blog post where we have it. So technically, if a user were so inclined, that they could go read through this sort of few paragraphs and figure out what exactly is going on. But you're very explicit about it, and I think that's not accidental, but that's also something that's a philosophy in Chrome, for example. So Chrome is open source, and they're very upfront about exactly what they do. And since its inception, I think it was designed with security and privacy in mind. So it was natural to do it. We didn't have to go out of our way to do this, but it's very useful. Yeah.
All right.
All right. Yeah.
Thank you again.